Okay, this is Ken from Maker's Box, and we are going to assemble the ArduStryfe shield here. I always like to start with the resistors, and in this case we're going to start with the two blue 10K resistors. These are special. They're for the voltage divider circuit. They're blue because they are 1% value tolerances, where normally they're 5% value tolerances, and we've got special markings for them to show. And still kind of playing around with the values I want to use. So basically what we need to do is be able to detect the voltage of the battery, which if you use it on a lithium 2S cell will be 7.2 volts or more. And the Arduino itself is running at 5 volts, so we need to bring that voltage down just enough to be able to monitor it with the 5-volt system. So that's what this is going to do. And there's some math that tells us exactly how to do that. So this is not going to be a how to solder video. I'll put some links in the description for some of my favorite ones that show the close-up soldering better, but in general, keep your iron tip clean and hot, and want to heat up the pads and the leads at the same time. And you'll see the solder, if you get temperatures right, the solder will flow and tent. It's using capillary action to pull itself into the joints, which is kind of amazing to see. And I always like starting with the resistors because they're a little more heat tolerant as you bring your iron up temperature, and kind of like pancakes. The first couple are a little tough, but from there we'll go on. As you saw, I grabbed a batch of I think 5 10K resistors. These are the normal 5%, and they're 1/8 watts, so they're a little bit smaller packages. So we're looking for the resistor spots that say 10K on them, and we're using these for a couple different purposes. The first and foremost is for a pull-up or pull-down resistor, where if we have a digital signal that we're monitoring or controlling, if it doesn't have a driver to it, it will drift and float, and as it crosses over the halfway point, it will cause false signals. So we need to either drive at high or low depending on what we're wanting to do. And in the cases of the switches, we usually pull those high, and then the switch will pull the signal down to ground. And then in the case of our MOSFET switch that we're using to control the motors, we want to control that gate signal low so that it doesn't turn on accidentally until we're ready for it. So there's a 10K there. And then additionally, we're using 10Ks, and we have two Debounce circuits in here, which are resistor capacitor circuits that are using a couple of resistors and a single capacitor. And I'll talk a little bit more about them later, but for now we're just looking for 10K values, loading those up and soldering them. So if you're a little leery about soldering, if you haven't done it before, it's just something you got to get in and try. I actually have some kits that I've designed that kind of helps you get started if you're needing something to kind of warm you up. Get yourself good iron and just get some practice, you'll be fine. I've tried to design this kit to be as beginner friendly as possible. There's a couple little tricks in here that I'll show you that are a little above beginner, just because that's how it turned out. if you want to be a modder in Nerf, you're going to have to learn to solder, because if nothing else, you need to, if you're changing motors out or changing your batteries out, you're going to need to be able to solder those. And there's really just no getting around that. And it's a good skill in general to have. I hope you do things like repair appliances and things like that. And of course, there's all sorts of fun electronics kits just besides doing Nerf. If you want to add LEDs or something to your Nerf gun, there's kits for that. And just about anything you can think of. Soldering will open up a world of making for you. Okay, now you can solder these in one at a time if you want, but I will generally put all the resistors of the same value in at the same time, solder those. And I like doing that. I mentioned the heat tolerance and also the board. You know, you see how we're flipping it over and it's holding the resistors in place. And then I'm actually working from highest value to lowest value. So next down the chain here is some 1Ks. And these are part of the debug circuits I mentioned. Let's see, I think the camera's sliding in on us here. So there's two of those, so I'm looking for 1K there. Let's see, I'm trying to do this with two cameras, and one of them is kind of dropping in on me here, so we'll stay focused on this closer one. So there's a 1K. And I don't know if I said resistors, so they have color codes. When I sell my kits, I'll generally mark them so you don't have to look them up. I can't remember the color codes. There's just a few special values to remember. A red, I know, will be a 1K. Orange will be a 10K. There's online applications to help you look them up if you need to. And if all else fails, and I do this quite often, is just get your multimeter out and check it. No harm in that. I don't think anybody really expects you to memorize color codes anymore. Fortunately, in digital electronics, there's only a handful that you need to know. Like one, 10Ks is probably the most common. And then, okay, next down the line in our values here is a 330 ohm. And I know that 3 is orange, so it's going to be orange something. And this is a current limiting resistor for the LED. Red LED will have a 4 voltage of about 2 volts and a current of about 10 milliamps. So there's some math we can do on that to calculate the value. Will come out to be about 300 ohms, and 330 is the closest decent value to that. Resistors come in kind of set standard values, and selectors a 290 and a 330 and then a 390, I think. And, fortunately for digital electronics, there's only a few real standard resistors like 10Ks, and 330s are pretty common. Next down, and our final resistor here, 100 ohms, and this is also current limiting, but is for the infrared LED, and it has actually got a lower forward voltage than a red or EL LED, but also has more current at about 50 milliamps. So when you plug all those in, you end up with 100 ohms. And of course, this is what we're going to use to detect when our darts get fired. So it'll be an infrared emitter detector pair, and this will be the light source to help us figure out when that dart flies by. And so with that, the opening act there, we got all our resistors in place. Time to start paying a little bit more attention because we've got another circular package, but it is polarized, and this is a diode, and it allows electricity to flow one way. It has a marking on one end, silver, and that matches up with a marking on the silk screen. In this case, it is a kickback diode. When your motor or a solenoid is de-energized, the collapsing magnetic field will generate a spike in voltage, and that can damage the MOSFET that we're using to control it. So we're basically giving it kind of an off ramp to shunt that current around our MOSFET and keep it safe. And diodes have a lot of different functions, but controlling the flow of electricity is one of the main important ones. Okay, and speaking of our MOSFET, I believe it is time to do him up. And this is one of the tricks that I mentioned I'm going to kind of throw at you. We're going to use a surface mount component. The reason I did this is because the footprint for this is significantly smaller than the through-hole component, and given the constraints of the board, that was really just how I decided to do it. And I think what you can see is this is really not that difficult. So there's a large silver pad and two smaller pads, and that's going to match up with this larger pad and these two smaller pads. This guy will kind of move around a little bit on us. So one of the tricks is to kind of tape them down. Not a big fan of the devices and mechanical helpers. I do use I have a pair of tweezers and a vise thing that I use, but tape is one way to hold things down, and sticky tack is another one that I kind of like to use. This guy's a little bit tricky because he is designed to dissipate heat, which kind of fights against you when you're doing soldering. So you saw me blob some solder on there. Turn the heat up on my iron a little bit, see if that'll help me out. Clean the tip. So I'm getting that heat in that pad. I got kind of a liquid, and I'm going to come up and I'm going to touch the tip of that tab to make sure that heat's going into the package as well, and I can see it flowing beautifully right along the edge there. And then I'm looking at the feet to make sure they line up, and I think that flowed pretty good. Last time I did this, it was a little bit of a fight, so I'll come over and take a look and make sure it's up a little bit off the pad. So what we can do is we're just going to come back in, and I'm going to push down with some pressure and reheat the package, and you should be able to feel it kind of sink down in. And I dialed my heat back a little bit, so that's going to hurt me. And so this provides an electrical connection as well as a mechanical connection with the board. And I think that's as good as we're going to get it. So I'll let that go. And then all we have to do is come in and knock something onto the floor, make you wonder what it was. Come in here, we're just going to, so it's just like a through-hole component. We're going to touch the pad and the lead of the component, and when we introduce that solder, if they're both at the right temperature, it just flows magically. And again, there's number of videos on through-hole components, or I'm sorry, surface mount soldering, and this is actually a fairly easy package as far as surface mount goes, other than the fact that it's so big that it actually introduces some problems with the thermal. Okay, and with that, let's throw in the star of our show here, which is our ATmega 328. These come out of the factory with the legs kind of splayed outward, and I'm not sure why they do that. It's probably something to do with the way they mechanically sit in the board and hold themselves in, but what I generally do is just kind of push them up against a firm surface and bend them over. Try and get those legs perpendicular. IC chips always have a polarity. There's a divot or a dot. In this case, we've got both of them. And then if you look at your circuit board, you'll see a divot or a dot, depending on the designer. And with any luck, this guy has 28 pins, and if you bend even one of them, life's not going to be fun. So we're trying to get all these guys in at the same time. We're gonna, so if you buy this as a kit from me, I'll probably have already bent the legs because I have to pre-program the chips, and so you might be spared this part, but it has to be done. And there it went, and you always want to double check, make sure you didn't fold over any legs. And then I will come in and solder two opposite corners just to hold them in place. And then I will come back, and we want to verify, double check our orientation. So I'm looking, there's a divot on silk screen, and then looking that it's flat to the board. And boy, that wasn't, so I pushed it down a little bit, and now we're good. The reason for that is being once you solder more than one leg in there, it gets exponentially harder to undo your work if you get your chip in backwards or it's not sitting correctly. And so this is one of those cases where just a little bit extra time will pay off big dividends. A lot of times if I get a package in backwards, and I do it more often than I'd like to admit, it's just easier to kind of clip the leads off and unsolder them one at a time than to try and save the chip. ATmega kind of exception because it's, you know, it's a several dollar chip. It's not cheap, so it's worth a little bit of effort to salvage, but an AT Tiny or something just might not make the cut. It's just so much easier if you get it in correctly the first time. There are a lot of times you'll see a socket that the chip will fit into, and that will help you. And like the Arduinos, like the Uno with a dip package will usually, not sure so much anymore, but in the olden days they were always socketed, and that certainly helped out with if you blew one up to be able to replace it easily. So we've got two sets of capacitors. We've got some 0.1 microfarad and some 1 microfarad. Let's continue with our highest to lowest. These are a cut tape for machine feeding, and sometimes a little hard to get off there, so I usually just clip them free without trying to pull too much. These 1 microfarads are part of the power regulator circuit. We're using an MCP 1702 to take the battery voltage and get it into a 5-volt regulated system for the microcontroller. And for that, we need a couple of extra capacitors just to stabilize the circuit, and that's always kind of dictated by the component's data sheet. There'll be an example circuit, and if if you're an engineer and smart and know how to do all the math and stuff, you can figure it out yourself. Or if you're just a hobbyist like us, you can follow the example circuit in the data sheet, and you usually come out just fine. I don't know how many times I've had trouble with a circuit and I've gone back and reread the data sheet, and sure enough, the answer is right there in front of me. Okay, so now 0.1 microfarads. We've got these are going to be used. I talked about the Debounce circuits, so 2 of those are for that. One of them is for power filtering the line to the microcontroller. Again, kind of part of keeping the signal clean for the digital electronics. And then additionally, we have one that's part of the reset circuit that helps when you're sending a programming signal and you need to reset the circuit. There's a little resistor capacitor circuit there to help get that going. Okay, 0.1. Kind of snuck these in just a little bit everywhere. I believe this guy is for the AT Mega. Yeah, probably should have done those first. So I'm going to come in, worried about them falling out. I'm just kind of, there went one of them. Just splaying those leads out. Just a hair to hold them in place till we can get them soldered. What we're really trying to do is keep everything kind of at the level of the chip here, and we're doing that because of the way that it sits into the strife. We're putting some components underneath the board and kind of tucking them out of the way so we're not interfering with the magazine and things like that. You and you. So the debounce circuits, I mentioned that a couple of times. On the mechanical inputs, like the switches for the rev trigger and the button if we use it, those will actually, if you look at them on a very short time scale, will have a jittery signal as it transitions from high to low or low to high. And that's just because of the mechanical system, and it happens very quickly. And normally it's not a problem, but in cases like with the rev switch where we're using interrupts, those mechanical or the quick electrical transients can actually trigger the interrupts multiple times before the signal actually stabilizes. Okay, let's throw our speaker on here. Again, another cut tape, and these will actually, I've pulled these actually apart before. It's one of the reasons you'll see me cutting these cut tapes off instead of trying to physically pull them apart, is because sometimes it'll damage the package. This particular piezo speaker doesn't have a polarity. Sometimes they will, depending on the manufacturer. These are from TDK. They're PS1240s, and they don't. And I really like them. I use them at soft circuits and some of my other, like my TARDIS pin circuit. So, and we're just using it to provide just a little bit of audible feedback, like when the system starts up, or if you leave the blaster on, it's going to beep once a minute just to remind you. Okay, so we are ready to put in our power regulator. Again, this is an MCP 1702, and it brings that battery voltage down to the 5 volts that we need for the microcontroller. Sometimes these packages will sit up in the air a little bit. We want this one down as close as we can, kind of keep things level. And leads are fairly close together, so you're going to have to kind of be careful with your tip and your solder. And if you manage to accidentally bridge bridge over, then you come back in with some solder wick and remove it, or some flux will help. We've got a few more components that are going to have close leads, and I'll show you on one of those on how to do that. So getting pretty close to being done on this side of the board here. We do have our fuse here. It says PTC. If you're just doing AA batteries, you can use the fuse out of the Strife and put that in here. I've got a 2.amp fuse here, which would be a little bit more appropriate for if you're using lithium batteries, or something with a little more oomph to it. And these are they heat up as if they get too much current through them, and they'll open up and throttle down on the current, and then when they cool down they'll reset. So they're great if you get like a dart jam and your motors go to stall current. They will shut those down in a matter of seconds and keep you from overheating. So I'm going to fold that down so it's flat in there, and I've left the markings on the upside so we know what value it is in case there's a question later. Got one other component we need to do similar to that, and that's the resonator. And this clocks the microcontroller, and we're going to have to fold it over just a bit to get it to be flat like we want things. So the microcontrollers themselves can run at a number of different clock frequencies, and the ATmega itself can actually run up to 20 megahertz. Arduino just kind of stayed with 16 megahertz. The original ATmega 8s were clocked at 16 megahertz, clocked at 16 megahertz. So that's kind of been the standard from Arduino from on. And they actually have an internal resonator that will operate at 8 megahertz, which I'll use sometimes on battery-powered devices. Kind of saves a little bit of current. In this case, we're actually going to put the bootloader on it, and we want it to behave just like an Arduino Uno. So we're going to use 5 volts, and we're going to use the 16 megahertz just so we get those behaviors. And with that, I think we're done with the front. So if we flip it over, and this is going to be the actual side you see facing upward, and let's put in our Hall effect sensors here. These detect a magnetic field, and we'll put little magnets on our clips, and since there's 3 of them, we can detect what the capacity of the clip is based on where the magnets are at. They have kind of a D shape facing up with the, you'll see some markings that tell the value of the chip. They're going to go here. There's U3, U4, and U6, and we're going to fold them over, and there's some markings to kind of show you where they go. And then there's the digital pins that we're actually using to read them is D10, D11, and D12. So these are going to splay out just a little bit and then fold over. And so when they fold, we're trying to get them into that rectangular marking, and they don't have to be perfect. That's just guidelines, and we're trying to get them flat because again the clip is going to come up over them at this angle. And let's throw solder on one lead here, and then come back and just double check, make sure we're in the ballpark. Yeah, I think that's about as good as we're going to get it. And let's go ahead and just get the rest of these in here. So these guys are a little unusual. So I used a Hall effect sensor for my Geek Spinner kit, where it measured when the spinner was rotating around, it knew when it reached a certain point, and that required a unipolar Hall effect sensor, so you had to know which way the magnetic field was pointing, which required me to know which way the magnet was on the cap, and that was quite a hassle. And I wanted to use these guys. These are omnipolar, so they'll react to either a north or south pole. But in addition, they have a special feature for power saving, where they'll only check the for the settings about every 100 milliseconds, which they're designed for like checking if a laptop lid opens. And so 100 milliseconds on the human time frame is pretty rapid, but for the case where the fidget spinner, the rotations on those were much faster than 100 milliseconds, so that didn't end up working out okay. But we ended up using them here, and so the omnipolar means that we don't have to concern ourselves with the orientation of the magnet on the clip. It just has to be a north or a south magnetic field, and that kind of makes life easier on those geek spinner kits. I actually ended up gluing the magnets to the caps ahead of time because it was such an error prone. Even I had trouble getting them in the right orientation 100% of the time. So I want to kind of remove that hurdle for somebody doing the kit. And put those guys down. It's a little unusual to have components on both sides in through-hole kits. You see it all the time in surface mount components, and in this case, we're it's a special circumstance because we're trying to tuck a lot of this away from the action, but we do need a few pieces up here so we can measure the clip being inserted, and then we're going to have all our wiring come in and for these connectors, which is really the last piece we have here. So there's a number of connectors across the top where we're going to bring in our inputs and our outputs. I guess this is work our way left to right here. So the photo cell is in the front end where we got the infrared emitter and detector pair. So we end up combining a couple signals so we get only 3 lines. These do have an orientation. You see they're kind of offset inside, and they're polarized connectors, so they have to sit correctly or life's not going to be good. So we want them to sit right in their footprint there. And these have about the same spacing pinout wise as the a little tighter than our voltage regulator. So again, we're going to have to be kind of careful on our tip control. And I am using kind of a big fat chisel tip, so if you've got a thinner tip, that's going to make your life a little easier, but it certainly is possible with a regular tip. Okay, so this 4-pin connector goes up to the display. It's actually an I2C bus, which has a power, ground, and then a data and a clock. And there's a number of different components you can run off I2C, but in our case we're using it to power that display. And so I'm going to go ahead and I'm just going to bridge over 2 of those. Wow, it's actually not working. I'm not able to bridge because I got so much flux on there. So that's kind of wanted to show you. So the flux is in the core of the solder, and then you can buy flux separately to add, and it certainly makes life a little easier. Just kind of yep, see, I'm trying to bridge it now and I can't get it to bridge, so hats off to flux. So in the case of if I did get a bridge, I would bring in my flex pen and add some flux, or you can use your solder braid and come in and remove a little bit of the excess solder. That's kind of silly where I'm not able to actually mess things up. So the debug, we'll show you as we get building a system that can either be a button, or we use that to trigger the debounce screen so we can see what the various readings are. And the operation varies based on whether it's detected on startup or pressed later. And it looks like I forgot to set out a couple. Oh, I got them kind of hidden over here. But you can see that's really all that's left as we kind of finish up here. The rev switch, the LED, and the clip. And these are all going to be signals that will come in. And the reason I put connectors on here is just it makes life a little bit easier for assembling and for troubleshooting. And if you've got to solder your wires in there, there's a little bit of a reliability issue. As they wiggle around, they might break. And I just decided to go with the connectors, and these are Pico blades from Molex. And that's a whole other story on how I ended up selecting those. But so in general, so I got 2 more of those headers to go, and I got to dig them out of a bag, so I won't keep you around for that. But final kind of things as I finish the circuit board, there's a lot of flux on here from the solder, and that can be cleaned up using isopropyl alcohol, or I like Goo Gone. Rinse it off. The only things we got left to hook up now are just to integrate the blast. We got our motors connection, our battery connection. We got ISP header if we want to reprogram it. We got FTDI header if we want to reprogram it. And then we've got 2 mechanical through-hole parts that are going to be held on by the screws that were used for that wire cover. And so what I'll do is, after I finish it, because I've been talking and been kind of distracted, I'll come back and kind of examine each joint, make sure you don't have any bridges or missed any solder connections. I don't know if you guys saw earlier where I had a capacitor fall out because I forgot to solder it in, but we got that fixed. So just double check everything, and then when you initially power your board up, you're always watching very carefully to make sure that nothing that's behaving the way you expect, and you're feel around, make sure nothing's getting super hot, and you want to unplug it quickly if it is, and do your troubleshooting. But if all goes well, I think we are ready to integrate this into the circuit. So hopefully that convinced you that this is quite doable.